Hello and welcome to Science Never Stops. I'm your host Joseph Vick with the U.S. Space and Rocket Center, and May the 4th be with you. Today we are celebrating May the 4th, so I have my two lab assistants with me here for the video. But what better day to talk about Sir Isaac Newton and the laws of motion and forces. So the forces applied to all objects and causing their movements. So Sir Isaac Newton is I would say probably the most famous or one of the most famous scientists of all time, with his works ranging from optics, inventing the calculus, discovering like the different laws of motion and gravitational pulls upon objects. So he was a brilliant individual that sort of paved the way for what physics is today. And on May the 4th, let's talk about some forces and how we can apply those forces. So let's get started with our setup. So what you'll need to look for in your kitchen is kitchen twine or string. You'll need Ziti noodles or a round noodle with a hole in it. And you'll need something to attach those noodles to so that we can zoom them across. So let me get my setup ready and show you what it looks like. And let's begin. Now, for our experiment today, we're going to be talking about forces. Now, a force is a push or a pull on an object. And for our push and pull experiment today, we're going to be using our Newton noodles. So I have a Ziti noodle here. You can use other type noodles as long as it has a hole through the end of it. So you can take string, you can cut your string, and put your noodle through it, just like you're putting a bead through a string. Just like that, and you can see as the noodle zooms across. So we're going to be doing, with noodles, experimenting to see the three different laws of motion that Sir Isaac Newton did so many years ago. So let's get our Newton noodles all set. I happen to have my spaghetti and white rice containers because they're tall and they work with stretching out the experiment in front of me. So I'm just going to cut the string. The string can be as long or as short as you need it to be depending on how wide your setup is. You don't have to tape it to anything. If you have a lab assistant that is there and can hold the string, that works too. So notice here, I have the noodle and I can zip it across, back and forth, just like that. So that is our setup. So I am all set up. So I'm going to start with the first law of motion. For Newton's first law of motion, objects at rest stay at rest, or objects in motion stay in motion, unless you use the force, or a force is applied. So notice the noodle on the string. The Newton noodle will not move at all until a force is applied to it. Now, the Newton noodle will continue to zoom across the string until it hits the other side, causing it to stop. So let me apply a force to the Newton noodle so that you can see that an object at rest will stay at rest until I apply a force. And then once that force is applied, an object in motion will stay in motion until another force will stop it. For Newton's second law of motion, we have two new variables to work with: mass and acceleration. Now, note the rather large mass of the cardboard tube there in the center of the table. And in front of the cardboard tube, you have the small noodle, or representing the small mass. And in Newton's second law of motion, it's the acceleration, which is the movement of an object, depends on the force acting on the object and the mass of the object. So if I use the same force to accelerate the paper towel tube, which is the large mass, and push using the force a noodle, which is a small mass, the noodle will have a greater acceleration because the noodle has less mass. And another example, it's easier to push a toy car than a real car. The force I'll need to apply to a larger mass will need to be greater because of a greater mass to cause acceleration. But if I apply the same amount of force that I applied to the large mass to the smaller mass, an even greater acceleration will result. For Newton's third law of motion, for every action there is an equal and opposite reaction. Forces always come in pairs, equal and opposite action-reaction force pairs. The size of the forces on the first object equals the size of the force on the second object, and the direction of the force on the first object is opposite to the direction of the force on the second object. And to showcase that, notice there are 3 Newton noodles on the string, 1 separated on the left and 2 together in the center. I will apply force to the Newton noodle on the left separated. The force applied will hit the noodle in the middle. The force will transfer through, and an equal and opposite reaction will strike the other noodle, and it will zoom to the other side of the string.
And remember, science never stops.